When you're solving some trig equations, you're going to be required to use the zero product property. This is something that you first started to learn about back in Algebra 1 probably, well even prior to that, but we really started to utilize it in Algebra 1 when we were factoring. As a reminder, the zero product property says that if you have something times something else and it equals 0, then one of those two things has to equal 0. So if A times B equals 0, then either A is 0 or B is 0. And we utilize that, like I said, when we would factor. So if you took a quadratic and you factored it, and let's say you found x minus 2 times x plus 7 equals 0, then you would take this x minus 2 factor, set that equal to 0, and the x plus 7 factor, set equal to 0, and you would get solutions of 2 and negative 7, because those would make either of these 0, which means the product would be 0. So we're going to utilize that. When you have something times something equals 0, you set each of those individual factors equal to 0 to solve. So you can see in example 4, we still have a trig equation. We have the secant of x times the quantity 2 times the cosine of x minus the square root of 2 equals 0. And I can see that this is a product. We have the secant of x, this is our first factor, times the 2 cosine x minus root 2. So if this factor times this factor equals 0, then what has to be true is either the secant of x equals 0, or 2 times the cosine of x minus the square root of 2 equals 0. And we would like to solve for both of those. So think about if the secant of x equals 0, which is 0 over 1, then the cosine is the reciprocal. That would mean that the cosine of x would have to equal 1 over 0. So is that possible? It's not. Or if it helps you, think about it as the secant of x is equal to the 1 over cosine of x. Is it possible to do 1 divided by cosine and get 0? It's not possible. So in this case, we're not going to get any solutions from this factor being set equal to 0. So that means over here, I might get some solutions. So again, I'm trying to solve for x. So I'm going to isolate the cosine of x first. So I'm going to add the square root of 2. So 2 times the cosine of x equals root 2. And then I'm going to divide both sides by 2 so that the cosine of x equals root 2 over 2. We're looking for angles that have a cosine of root 2 over 2, and our answers have to be on the interval 0 to 2 pi. You're going to see me draw lots of circles like this. I encourage you to do the same thing on your paper. I know that cosine is root 2 over 2 at pi over 4. And then cosine is also a positive root 2 over 2 here in the fourth quadrant at 7 pi over 4. So my only solutions here come from this part, this factor being set equal to 0, and my solutions are pi over 4 and 7 pi over 4. It's impossible for the secant of an angle to equal 0, so that's why this part didn't give us anything. So these would be our only solutions. Now, what makes this, more challenging is this problem here. It looks pretty intimidating because it's not factored already. But here's what I want you to do. Anywhere that you see a cosine of x in this problem, I'm going to replace it with a w. I'm just picking a random letter that doesn't already show up. I didn't want to use x or anything like that. So imagine if this is just cosine squared of x. Notice we put the 2 with the cosine because it's not cosine of x squared. It's the cosine squared of x, and then the cosine of x here. This is a quadratic, right? If I replace cosine squared with w squared, I would have 2w squared minus 7 times cosine of x is w plus 3. That's a problem that you all know how to factor, right? You could split the middle, however you need to go about doing it. I'll show you one time right now how to split the middle, but I'm expecting that you're all comfortable with factoring. So 2 times 3 is 6. I need factors of 6, so 1 and 6, 2 and 3. I could also use -1, -6, and -2, -3 because those are also factors of a positive 6. I need to pick the pair that adds up to be this coefficient of this middle term, -7. which means we would use -1 and -6. So we are going to split that middle term. So 2w squared minus 1w minus 6w plus 3. I didn't change the value of the problem. I just made it have more terms, right? If I combine these back together, I would get back to the original problem. But this is beneficial because it has 4 terms and I can factor by grouping. So out of this first group, the GCF is w, and I would have 2w minus 1. Out of the second group, your GCF is either 3 or -3. But our goal is for this to also be 2w minus 1. So that means we'd be factoring out a -3. So each of these has a 2w minus 1. So we factor that out, and we are left with w minus 3. So this is how this quadratic factors. But remember, this is not the problem I'm solving. So now as soon as it's in factored form, I'm going to replace w back with the cosine of x. So the real problem here, instead of 2w minus 1, it's 2 times the cosine of x minus 1. And instead of w minus 3, it's the cosine of x minus 3 equals 0. So this right here is the factored form of our original problem, which is really what we're working on. This was just a way to get us there without it looking so crazy intimidating. So now we have a product set equal to 0. So that means that we have to set each individual factor. Well, it's 2 times the cosine of x minus 1. We set each factor equal to 0. Cosine of x minus 3 equals 0. So here I would add 1 and then divide by 2. So the cosine of x equals 1/2. And over here I would add 3. So the cosine of x equals 3. I want all solutions, but anytime that I'm working for all solutions, I start out on the interval 0 to 2 pi. So let's picture where all of this happens. So first, the cosine of x is 1/2. Where is your x value 1/2? A positive 1/2 for your x value occurs here at pi over 3. And then it also occurs down here at 5 pi over 3. So on the interval, just on the interval 0 to 2 pi, we could say that x equals pi over 3 and 5 pi over 3. But again, this isn't all solutions yet. That's just on that single interval. And then over here, the cosine of x equals 3. Well, is that possible? Are you ever going to have an x coordinate on your unit circle be 3? The answer is no. So in this part over here, we're not going to get any additional solutions. So now all I have to do is figure out how to write this, not just on the interval 0 to 2 pi, but what about all of the coterminal angles to pi over 3 and 5 pi over 3? So again, the quick way to do it is take both of those and add 2 pi n times. 5 pi over 3, add 2 pi n times. There's not really a shortcut here to write all of them because they're not directly across from each other. So you couldn't just take one and repeatedly add pi, for instance.